Hello, good evening, and welcome to the third Better AI meetup. I feel like it's actually the first because for the past two meetups we didn't have anyone in the audience, so I'm very glad to see you and hear you all, and I'm looking forward to your questions. Before we start, I would like to thank the partners of this meetup, which is Hub. It's the place where you are currently staying, and they are aiming to build collaborative spaces, and collaboration is really what the Better AI meetup is all about, to connect researchers and AI enthusiasts and builders and entrepreneurs and create a community that will make Slovakia better in AI and machine learning. The other partners are Kinit, Kempelen Institute for Intelligent Technologies, and Innovatrix, a Slovak biometric company that's using AI and machine learning to create world-class biometrics. Today we'll be talking about, I think it's only proper when we first have real humans here. We will be talking about what actually happens when AI meets humans, and we'll have the guests which I'll introduce in a moment. So hello and welcome. Today we will be talking with two people. We will have an interview with Professor Jana Koshitzka from George Mason University. She's a professor of computer vision, AI, and intelligent technology. I think we have you on the stream. Good evening.
Good evening.
Yeah. But first, we will talk with Jakub Mertus, who's with Tatra Banka, and he was actually for the past few months and years creating something that's very interesting, and that's AI algorithm that should be actually better at trading than humans. So Jakub, it's your turn. Show us what you've been doing in Tatra Banka.
Thank you. Good evening. Yeah, I would be a bit careful with the terms of being better than a human, but simply stated, what we wanted to explore is to see if an algorithm can learn a useful trading strategy. So a first question to ask ourselves is, why should a retail bank like Tatra Banka care for trading? Why? Well, because we believe that it is in our core competence to take care of our clients' money. Yeah, but why? You have brokerages, you can do it yourself. Well, because retail investors are notoriously very, very bad at making investment decisions. And we're very well aware of this. For example, a recent study of eToro traders, daily users, found that nearly 80% of these customers has lost money over the last 12-month period, with a median loss of 36%. And this was a very huge upside market, couple of last years. So you might think how it looks like in a general when the trend is downward or when the market is moving sideways. This is what the trading looks like. You have memes, you have social media, which are giving you all these amazing investment opportunities, trading signals. You have pages on Instagram, on TikTok. So this is really something that a retail trader has in mind when he's going into investing. That's why we think that it's our core competence. And another topic, another question we can have is, this is so cliche for a data scientist to go into, like, can I make money using AI trading? Why should we talk about this? Well, yeah, it's true. These are some screenshots from Medium, from Towards Data Science, and there are just so many of these not very well formulated, not very well researched articles about how can one make, stock portfolio or using neural networks to do stock predictions. So it's all around the place. This one is a perfect one. It says, data reveals the stock market crash is far from over, and it's dated on 29th of March 2020. Where was it? It was here, right down there. That was when 29th of March happened. And from then, we had an amazing upside of nearly 120, 130% on S&P. A little bit of about how portfolio management in the bank regularly works. There are some key components to portfolio management. You have strategy. what kind of companies, what kind of sector do you want to invest in? Either like large European retail, for example, or some medium or large cap US companies. Then there is the risk appetite of the client that you have to take into consideration. So, for example, what is the ratio between equities, which can be very risky but have a lot of upside, to some bonds, government bonds or corporate bonds? How are we going to mix in some cash, commodities, or alternatives? And in the end, there is the algorithm itself. So we have something like modern portfolio theory, which is still very widely used and is still one of the algorithms that is performing very well with bits of tweaks currently. So in general, a portfolio management is going from here, which is some sort of a pie chart of these assets that you have in your portfolio, to next week, where it looks like this. Small changes in small time frames over a longer period of times. But in general, trying to not lose you money. That's very important, because retail customers are really good at this. So for the key components of portfolio management, the first two ones we cannot touch really. That is something that is up to the risk appetite of the client and the strategy of the managed fund, for example. But we can touch the algorithm. We can use some sort of strategies, even quantitative ones, where machine learning is involved, to see if we can do individual predictions and maybe save the performance of the fund in bad times. So one of these very important strategies, the algorithms, is mean variance optimization. So you have this return estimation and volatility estimation together. You say that, okay, you want to optimize for the highest Sharpe ratio, for example. But in the assumption of these classical mean variance optimization type algorithms is that there are historic returns that are predicting future returns. But this should not happen. That's a disclaimer in every single one of the normal managed funds or brokerages. Okay, but let's go further. So this is the important one, which I really want to talk about. We have the story. The story about how, let's say, a crazy enough student felt like he can make a dent in a field, right? So that's me going into work. And I go and see my boss and I say, okay, Daniel, I think we should focus on this topic for our data science, for our new data science team. And he was like, probably skeptical at first, as everyone should be, right? But he was like, okay, show me what you got. Then, after the first, let's say, classification algorithm, trading algorithm was developed, we went to our asset managers, portfolio managers, and tried to tell them that, okay, you can do this with machine learning, but they didn't want it at the time. They didn't know how to utilize it. They didn't understand it. But we were persistent. And even though nobody wanted the solution right now, we went ahead and made improvements on our own. Now the bank wanted to find the new sources of revenue. So my boss's first question was, how can we do this? Jakub, give me some idea. And I was like, okay, I have an idea. I know it's here in the drawer. Let's do some trading. And again, we went for the board of directors this time, saying that this is one of the ways we can make money. And they were like, no, we recommend you to focus on other areas, such as natural language processing or CRM. And this date is very important. This is March of 2020, when the Corona market crash happened and market did an oopsie. And a month afterwards, 2 months afterwards, the traders are back, asking questions, how does it work? They remembered that there was quite a limited downside for the strategy, for the algorithms, and they wanted to see more. So we came with this graph. So this is how it performed during the Corona crash on S&P, and this was actually out of sample. There was one of the models that we had in the bag previously saved that didn't want to, so we just did some inference with the new data. What they saw actually made sense to them. That okay, there is some limited potential. They might be trying to use it. So for some period, we tested them out of sample model performance, so-called paper trading with our traders. And 1 year later, they were confident enough to put the model into operations as soon as possible, as fast as possible. So then the operational challenges arose. But I will talk about them in a few minutes. So now some live fake trades in September of last year were done, where we test the whole process pipeline, where we were catching bugs before putting clients' money at stake, and this period took about 4 months of this live fake trading being done. And this is when we went live, just at the end of the last year. So what does it mean going live? And what are the challenges of incorporating a machine learning model into an existing asset management process? So there were 3 main challenges, but all of them had their pros and cons. So a challenge was, for example, that there existed no automated connection to the brokerage. So no API where we could just communicate with the broker and let some execution engine take care of the trades. But this was actually a good thing because we didn't have to program it, right? We didn't have to test it because there is lots of actual things that can go wrong in an execution engine. There were no data APIs that the brokerage was offering or that the guys from Tatra management had. So, but they were using, Excel add-ins from Bloomberg, which are highest quality data sources, and again are getting some cost savings into the whole process. And there was a last bit of a challenge because there was a lot of manual processing had to be done. A allocation of a portfolio manager's time had to be done, but there has quite a lot of upside, to have a person. There is a safety element, human in the loop. There is an easier adoption of these ML techniques by the business itself, and an expert can verify these quantitative results, right? But this graph shows it maybe very clearly that for a data scientist, this whole story, this whole timeline was a bit of a nightmare. You have that bit of data sciencing going on where you play around with models and you do some data feature engineering, but that is quite complex. But time effort is, limited. Let's say you can bang it out in a half a year, let's say. But then there was a development of some production code we had to do, something that was going to be touched by these managers, and there was the sales, the actual getting people to actually use it, the business. So you see that the actual time scale was approximately 2.5, 3 years. So that took a lot of time effort, but not very complex thing to do. So let's talk about the algorithm. That's something that you might be actually interested in, a bit more researchy. So what does the algorithm do? And I would say it's quite simple. There is the data going in, and we are using only price data. We are using daily periodicity, and it's not big data, right? So you have only that many days since, let's say, year 2000 or 1990. So you don't have these huge data sets that would be a problem maybe and would need some other, let's say, deep algorithms to be working with it. How did we define the target? Well, the target is something that is actually, the crafting the target is very tricky. Target can be something fixed time horizon, can be volatility based. You have to take into account real stop losses and take profits for the asset managers that they would use. But in general, there is the target which is moving with the volatility and with the take profits and stop loss. So it's not just like fixed horizon. And then there is the feature pre-processing. So the price data is trending. So it's a price, right? So it goes up, it goes down. It's not stationary. That's a problem. There is new data coming in from the markets, and the model did not see it in the training procedure, so it will not know what to do with it. So we have to ensure stationarity, but we want to keep as much memory as is possible. And I will show you on some graphs on how this is done and what it looks like when you do this pre-processing part, which is very crucial to it actually work. So first, the top one, that's the price, right? That's the future. That's a future contract on an S&P 500, a CME mini contract. Then you go down, you do something that's called finite fractional differencing. You make it look a bit better, but still not not useful really. And then you do something more to it, some sort of window, rolling window metrics, you normalize it in time, and you have this transformed, finitely, fractionally differentiated time series. Now compare the lowest graph with the one on the top of this one, right? So that's a daily percentage change. And it looks like a noise with some volatility clusters. So instead of using the top graph on this, we are using the lower graph of this, right? The lower data on the lowest graph. And that has some structure. That is still stationary. This one, that's just noise. But it's actually an important noise because that's how you do some sort of estimates of the barrier size which you use for the target definition. So in the time, like I said, the barrier is changing. Sometimes the barrier is very wide because we have volatile times in the market. Just like right now, there are big drop-offs. That's when you don't want to be too strict about your barriers because you know that intraday you can go either way, up or down, but you want to keep it so that the algorithm doesn't hit the prediction doesn't hit, the trade doesn't hit the stop loss or the take profit, and we'll end up somewhere positive, somewhere where the model predicted. And the other part of the algorithm, a bit more machine learning, is that we used a support vector machine, a classifier with a Gaussian kernel. We did some sort of bagging ensembles on top of that. And the trading strategy itself is very important because, for example, we didn't want to go short, right? We had to somehow prioritize our trades for our risk appetite, and that's what we figured that we can somehow do. There is a negative signal coming after a positive signal comes in the market. That's something that invalidates the last positive signal, and that's where we close the position. So not only the data has to be somehow pre-processed in a way where information is still attained, a correct kind of machine learning model has to be used in order to learn something and fit something, but not overfit it, obviously. But on top of that, you have the trading strategy, which is actually running and using that classification outcomes. Now, these are some graphs for out of sample data. So the reality is that the data is very noisy, and that's something that you don't necessarily see in classification algorithms, the results of a classification algorithm. But the ROC curve, the characteristic, I think that's a perfect one, for us. That's enough to give you a bit of an informed edge on what's going to happen, and to make these selections, which may in the long run give you an opportunity to make some money for the clients. And then there is this precision and the threshold where we are setting, okay, we just want to go with the very certain trades, and then we see that if we go further with the threshold, with the, let's say, some sort of probability proxy, then the precision for that is increasing. Again, not dramatically, you will never be very certain, and there is a baseline of where the market went, and let's say in 2021, the market as baseline was very high, the market was going up all the time. That's where your baseline is basically 64%. But we can do a bit of percent, couple of percent better, right? So this is a cool graph showing you how it looks like. So you have some sort of instrument price data. We use and we trade only on 2 instruments currently. We are doing some sampling of the data sets, and we have a lot of these samples. Then we have a lot of the super vector classifiers. They all give you some sort of they all give you a prediction. We average it, combine it. That goes to the trader. Now, that's a part of the actual smart fund. So right now, this is a live strategy that we are using as part of one of our biggest funds in Tatra Banka, in Tatra Asset Management. Tatra Asset Management thinks that it is actually the first asset management company in Slovakia which uses this sort of machine learning or AI strategy or classificator in one of these funds. So a small fact sheet on the smart fund. The at the beginning we started, and there is a 10 million allocation, approximately 5% of the assets in the fund being dedicated to the strategy. And we are actively trading two assets, both futures. And the model, is inferred from on a daily basis, like I said. And there is a portfolio manager which is dedicated to running this model every morning, giving in new data to the model, a bit of manual labor. But this is actually a good thing. We are starting small. We'll be reevaluating and seeing where it goes from there. So what are the main takeaways from this short presentation I would like some of you to remember? So a bit of some takeaway for some leaders or executives. Building data science capabilities is a long journey. Like in this example, it was 3 years basically, and mitigation of these obstacles is a key success criteria. For example, if it wasn't for my boss who managed to give me enough time to work on this, although no one wanted it at the time, it wouldn't have happened. For the data scientists, for the machine learning experts, don't use overkilled models, deep learning, and some sort of neural networks, some LSTMs, just to be, sort of buzzword compliant. We found out that the neural networks don't work at all at this. It looks like that the non-convex optimization and the structure of the cost function is not really well designed for this type of problem. And for the business people, be patient. It takes time, trust, and effort to put these kind of new modeling techniques into operations and seeing the results. Again, like it took us 2.5 years, and right now we are just starting to see the results, which are actually quite promising. So let me answer this question. Can an algorithm learn a useful trading strategy? Not better than a human, probably. It's very hard, but we will see. But we are hopeful, and we are still doing improvements, and yeah, more will come.
Okay, thank you, Jakub, very much. I think that we will see that it's that the algorithm actually works, because I just realized that I have money in the fund. So
oh, really?
Yeah. So
okay.
I'm betting on it.
Yeah, if it doesn't, it's just 5% of the allocation. So if that goes to zero, you just lost 5%.
I don't want to lose any percent.
Oh, okay.
But we already have questions. You can ask questions through Slido, or if you have questions here and want to ask like the real human beings, just put the hands up, and I will repeat it for the people at stream. But we already have some nice questions, so we will probably start with the most voted ones. If there are some questions after like 10 minutes, we will still answer them at the end. So don't worry, they will not get lost. So one of the notes I made was about the human in the loop component. So, and the top voted question is about it. So, can you somehow quantify the human in the loop component of your deployment, and how frequent were human interventions, and how often did they counter model suggestions?
Yeah. Okay. Yeah, that's actually a great question, because it ties into this system that was in place, of a manual kind of trades deals being done by these portfolio managers, and a suggestion, really, because it is a model suggestion. At the end of the pipeline, there is a suggestion of the model at this current day, and from these 5 months that's been live, I think only once did the portfolio manager disagree strongly with the prediction in a way that actually saved us a couple of percent on the trade. So there was only one example of human intervention, but it was a positive intervention, and that's something that these proprietary traders and dealers they kind of get a feel for the market. But in general, it's a strategy, and we don't want to touch it. In a way, we actually want to evaluate really out of sample. In reality, how does it work? And for that, it's best to not touch it. Yeah. And so quantify, you can actually put a monetary value on that single time when it happened.
Okay, this is great. again, AI. Sorry, we have a question in the audience. Yes.
I have again a question related to the humans in the loop. We now know that there were humans controlling the algorithm, basically. I'm interested to hear whether there were also some checks that are checking whether the human did his job right. Maybe beyond some simple like validations of columns, etc.
Yeah, I'll just repeat it for the people in the stream. We have a question about, again, human in the loop, and the question is, who was actually controlling the human that was in the loop? So, and what were the checks or let's say a framework in?
So these are generally very responsible people, the traders. They're ones of the most cool-headed, not stressing and all, chilled out dudes with a lot of responsibility that you can find in a bank. So they don't need much supervision, and obviously when these new strategies are being put into the funds themselves, they take great care when doing these changes, right? Because they have some system which is quite complex from operational standpoint and even from mathematical. So they really don't want these changes to happen. But once there was enough, let's say, proof, and these out of sample and these paper trades, the live fake trades, like I call them, being done, then that person was on board. That was the one that we had, created a friend inside the asset management, and he was very certain that this can work, and was the one that was driving it as well. So probably that's actually a very important part of it. You want to have this kind of business connection that believes in what you are doing, and it did take a lot of persuasion, but in the end he is the one who is like, okay, I will listen to the model and see where it goes.
Yes, thank you. We'll continue with a few questions. Did you also research other approaches for the trading and how they perform, such as reinforcement learning, which is currently a very popular approach? I mean, you mentioned already that you should not use all the buzzwords that are in
Oh, yeah, but you don't need to do deep reinforcement learning. So actually, funny story. For my master's in data science, my dissertation was on deep reinforcement learning in trading. so yeah, we did research other approaches, and the deep component is quite tricky. Given, for example, the data sizes. We know that it might work when you are sampling the data differently, but not a daily basis. Yes, it is very popular approach when I read the news as well and read these articles on different blogs, but it is actually a tricky one to put into operations. But I think there is a lot of potential in this, and in the future I think we will be looking at it again, because you have that component of the action actually being trained itself. But there is a lot of more overfitting which you can do.
Yeah,
that's it.
Thank you. And now maybe to a more business question. If you could ask the bank management, the board of directors, as you mentioned, for any reasonable resource to boost this solution even further, what would that be actually?
Oh, well.
More data, perhaps.
You know what? Actually, I think I was... Since I started talking about this in our data science team, I was always like, give us access to tick data, right? Give us access to level 1, level 2 data, which can be expensive. Let's say not for crypto, for example, that's kind of free, but for normal assets like equities or future contracts, this data can be quite expensive, and you need to have some sort of architecture underneath it where you would be saving it and sampling it in a way you want. So that definitely can cost money. And the other thing you can always ask for is more people, right? give me someone who can work with me on this, because for some time, it's been kind of lonely. Yeah, help is always wanted, right? But it's not always easy to ask for a full headcount in a corporation, in any company.
Yeah, that's right.
That's a lot of money, right?
Yeah. We will do one more question, but don't worry, we will still have another questions after that. Sorry, just this is a real nice one to actually have. Are you better with your approach than the passive trading or passive funds, the ETFs that are currently very popular, or are you just improving active trading? Because passive trading, or at least it's said that it has better returns than active trading, and also lower fees, which is what's drawing people to those.
Good question. Someone knows what they're talking about. It seems like these are actually very good, very on-spot questions. Well, yes, passive trading or passive investment has been booming basically since the great financial crisis through the uses of these vehicles like ETFs. And we see that, people from the asset management environment are not oblivious to it. What they do is actually, and what they think will happen is that this is a cycle, and historically you can show that passive and active investment, let's say, passive and active portfolio management are kind of oscillating in the time. So yes, last 10 years were very, very good for passive investment because ETFs has very low funds, very low fees in those funds. But we think that the active investment will come into the light again. Not so obviously everyone would like that. Yeah, asset managers would like that. But it is actually something that will change in the future. It's certainty. The time scale is maybe not. Active investing will be popular back then, and many managers will be able to make more money than passive funds. Yeah.
Okay, thank you, Jakub. It's been most interesting. I already feel much better about my money. If you have any other questions, don't hesitate to write them down. Please keep your question in mind, and we will come to those later, and we will also come to these that we already have, because now I'm very glad to welcome Professor Yana Koshitzka from George Mason University in Virginia. Hi.
Hi.
Okay. Yeah, great. So glad to have you here. We'll be talking about your work, but anyone, if you have any other questions, just write to Slido as you hear it, because we will be covering many different areas. Let's start with what you're actually working on. I mean, you're working at the intersection of robotics, computer vision, and artificial intelligence. And the combination is currently crucial for many real everyday life applications, let's say autonomous driving, home robots or household robots. What are currently the main challenges that are being solved in your fields?
Well, so I think definitely the most popularized application is the autonomous driving, and the field sort of made a lot of progress in these regards. And so I think obviously there are a lot of machine learning techniques used in this problem domain, but there are always scenarios which the systems have not encountered previously. So that's one aspect of the need for this continuous learnings and updates these type of systems require. And when it comes to deployment, these type of systems in real world traffic, when you have some mixture of human and autonomous drivers, there is some unpredictability factor. So some ability to model the behavior of the other drivers is also important. So this is in the autonomous driving setting. And I mean, in household robotics, there are still kind of challenges when it comes to kind of mechanics and design, along with the perception and control of these type of systems. It's sort of very hard to replicate and design robots which have similar functionalities than humans do in order to accomplish a lot of these sort of household chore tasks. So I think we are a little bit further away from kind of the true household helpers, as you might think.
I mean, I have a robotic vacuum cleaner, but I don't think that's a good example at all. So, but
Well, that's kind of a small thing, right?
Yeah, it's not what I imagine as a true household helper. But you just mentioned the unpredictability of a human factor and the fact that you need to model for it, which is kind of a paradox. How to predict the unpredictable. So how do you actually devise methods to incorporate this unpredictability of human factor into machine decision making?
Well, again, as is in many learning applications, these type of models have availability to the large amounts of data. So the challenge is to basically learn predictive models of this type of behavior. So if you have multiple traffic participants, you have an ability to actually predict the future, which it depends on the current mode of driving. It depends on the understanding of the environment, where the lanes are, where the pedestrians are, where the other traffic participants are. So these are kind of exciting machine learning challenges. But as with any machine learning problem, you have these kind of long tail distributions. You have scenarios which you have never seen. And, so you can have a sleepy driver, or you can have an angry driver whose behavior is definitely an outlier to these settings. So again, similar techniques than in other machine learning applications arise is this ability sort of to quantify somehow the confidences of the predictions of these models and adjust accordingly.
Okay, so in your research, how do you then prepare or test a situation the machine has not actually been trained for, that that is performing correctly? How does the real part actually work? Well, how to test the scenario that you have not been anticipating?
Well, so I guess one has to be thoughtful when it comes to the initial design, is to sort of build models which have sort of reliable predictive capabilities. So, so there are a lot of sort of interesting theoretical problems when it comes to associating confidences with the given predictions of the model. And so in the case of systems which have this kind of simpler input-output behavior, being able to get hold of these confidences is usually the first steps how to quantify the trust and the confidence into the predictions of these models. In case of models which are involved in some sequential decision making, it is not enough just to look at the prediction at a particular time step, but you need to sort of have some ability how to analyze the entire behavior, how to quantify the quality of the behavior, and maybe sort of associate some measure of trust. And then you kind of work backwards depending on how your model is designed. I think the models which have a little bit more modular structure, and here I'm really talking about sort of very complex models which have lots of components, not just the kind of a single black box model which is trained on kind of data from one particular domain. So this modularity of these very complex systems sort of also affords better tools and techniques for introspection and analysis of what went wrong, or quantifying better the performance of these models. Yeah, if that makes sense.
Yeah. Is this basically the approach how to avoid bad decision making? Because we are really talking about interaction between machines and people, and especially in autonomous driving, those can be fatal when bad decision making happens. How to actually devise the machine learning models so that you somehow minimize the possibility of bad decision making?
Well, so that's typically the objective to start with, to have models which minimize, kind of optimize the behavior, whatever the optimality criterion is. But I think it's critical to recognize or have tools and techniques where you can, in the deployment of these models, sort of quantify whether you are encountering behavior you have not seen before, or whether you have a situation which you have a low confidence in. And, in these situations, one typically can kind of relinquish the control to the human, or have some kind of safeguarding strategies that would sort of switch the system to other type of modes.
Yeah, it's basically going back to the human in the loop, just as we mentioned at the previous presentation. Okay, I assume that industry is one of the main drivers of research in your fields, and that's where you also get your practical data. What is currently the hot problem to solve, for example, in autonomous driving?
Well, so I think, there are problems which sort of, the chunk of the development is indeed happening in industry. These are especially the problem which have sort of problem domains which have non-trivial experimental and infrastructure counterpart, right? You often cannot afford, or it's much more challenging to tackle these problems in academia because you need, say, fleet of vehicles in order to do the experiments. But there are other industrial applications beyond autonomous driving, which are also very interesting and have a lot of potential. So these type of learning-based robotic systems are also being used in the context of various manufacturing applications, in recycling applications, where you really want to kind of offload some of the laborious tasks which humans have to be involved into the systems, into the robotic systems. And fortunately so, in these other applications, the safety factor is not that critical. So, maybe the suitability or the advancement in making this type of systems reality looks sort of a little bit more promising. But I guess I slightly diverged from the question. So you were referring to.
I was
you
interested.
Have a follow-up?
Yeah, I was interested in what's currently the hot big problem, let's say, in computer vision in general. But yeah, the robotics, especially in interaction with humans, is obviously a great idea, because you can see it in industrial fields everywhere, in automotive in Slovakia and in other places as well. So that was the part. When we talk about decision making and everything, this is something that probably lots of researchers here have met. In many domains, the machine learning approaches use the data that was curated or labeled by humans. Does this pose a problem for you in your domain, and how to prepare the data so they are not biased or flawed? Because this could obviously create problem in later decision making.
Right. So let me kind of first answer elaborate a little bit more on the previous questions when it comes to kind of hot topics which sort of people are currently interested in and studying. And some of these topics, specifically in computer vision, also pertain to these issues of developing approaches which do not require such a large amounts of labeled data. So, the initial advancements in classification and recognition relied on hundreds and thousands of labeled images, where the labels were solicited from Mechanical Turk workers. And these were really critical for that initial training of these large neural network models, which had over, say, 70 million parameters. And So there are some recent exciting advancements where sort of the community has kind of figured out how one can achieve similar performance or learn similar quality models using the so-called self-supervised techniques. So you don't actually need the labels in order to supervise the models in that initial, very data-hungry stage. You, of course, always need the labels when you need to sort of associate the concepts with images. But the number of labels is significantly smaller while you are being able to attain the same kind of performance. So I think this line of work is likely to continue, and it's sort of exciting and promising because it's opening opportunities to deploy these ideas in other domains where maybe labels are much, much harder to attain. So this is kind of the label intensive part. And then, yes, so when humans label things, they bring all kinds of biases. So this is a very broad discussion, right? Because one can take it in a lot of different directions. One can take it in the direction of just biases themselves or where the data comes from, right? So usually the laborers or people who are involved in the initial data collection stages come from certain demographics. They have access to internet. They're sort of educated. They sort of come from different social economic groups, and it's very likely that the data they collect is more representative of the social economic groups they come from. And so if you train some of these models on such data, these type of models will likely have the biases which also are preferring these groups to the other less represented groups. So these are, some aspects where humans sort of affect the quality of the models and then consequently the predictions the models can make. And I think community and both researchers in academia and industry are kind of starting to take these problems a little bit more seriously because, often the decisions made by these models, in many cases, policies are sort of guided by some of these predictions. Hiring decisions are being made by some of these predictions. So I think it is important to kind of be mindful of the fairness and lack of some of these biases. Yeah. So this is kind of some general thoughts on the data collection. There are also kind of strategies how one can monitor whether the humans make mistakes. Usually in many of these labeling scenarios, you have more than one person labeling the single data item. And so you're looking for some kind of consensus between the different labelers in order to sort of decide what the ground truth label is for the purpose of evaluation. Yeah. Question?
Yeah, I had a question that basically ties to the bias because it's like the other part, and that's the how to actually make the models transparent and explainable, because that's what probably will be asked in the future. It's being asked already, but if it makes decision that affects people's lives, we want to understand why it made such decisions, and we want to be able to explain that.
Right. So again, sort of the existing techniques vary a little bit depending on the domain. Okay. So I think, for example, this idea of explainability and transparency in the domain of facial recognition could be studied by kind of developing kind of complete kind of generative models of the data where you can kind of properly sample all possibilities and synthetically generate data from the parts of the space which is not covered by the real data sets. Okay, so there is kind of there are a lot of ideas in this space when it comes to this generative modeling, and then you can kind of understand how different attributes or aspects of the data are affecting different decisions, where the decisions could be classification of race or gender and so forth. So one idea, big idea, is this idea of generative modeling, where you basically try to fill the gaps which are not covered by real data. This is of course challenging because this is not easy to do for any domain, and the face domain is particularly favorable because the techniques for actually generating this synthetic data for face images are quite well developed. These issues of explainability and transparency, again, are a little bit different for the systems which are involved in decision making and predictions. So there, I think there is some emphasis on, instead of having these kind of black box models, which is very hard to gain some introspection over, is to kind of go for some modular designs and even sort of more traditional techniques where you can sort of explicitly state what the state of the system is, what are the uncertainties of the decision-making process along the way, and then you can kind of backtrack what are the observations which led to the decisions the system is currently presenting. So I would also kind of advocate a little bit not abandoning the kind of the traditional structured models, which the initial research have made a lot of headway with in favor of these neural network-based models, which definitely kind of suffer from these challenges of interpretability and explainability.
Yes, thank you for your answers. We have more questions from the people. So I will start with the, let's say, combination of practical and future-looking. Probably more people have encountered it because it's been voted highly. So my robot vacuum cleaner's navigation once become dumber after update. So do you have any concerns about using continuous learning in domains like autonomous driving probably for this precise problem that it will become dumber and actually drive much worse than before?
Yes, so this is sort of a little bit of a challenge. And I must say this is definitely very much at the focus of a lot of current research, right? And these problems of continual learning and how to sort of do it correctly are still sort of under investigation, and they're sort of driven by these basic observations that it is not enough just to throw the new data at the model, right? So you want to somehow trade off this aspect of the model, not forgetting the old data and then simultaneously sort of correctly accounting for new types of data. I think in autonomous driving, the architecture for this continual updates is kind of very carefully set up. The systems which people use are very modular. They typically have these kind of digital twin copies of the entire system, so they can very carefully scrutinize what went wrong and correctly adjust it, and also evaluate and make sure that the data is properly balanced, and then the predictions for all the previous things are sort of correctly working when the updates are being made. Mm-hmm. In other systems, this is a little bit more challenging. I mean, these type of problems one often encounters in search and recommender systems, right? Because these are also systems which are sort of have some of these prediction models running under the hood. And when a big update happens, if an update does not correctly account for the new data while still maintaining the performance on all the old data, obviously customer is unhappy because it simply changes the behavior of the system. I cannot comment concretely on the vacuum question, partly because it's not entirely clear to me what kind of updates have been done and what it means that the vacuum cleaner is not as smart as it used to be. But, these are all kind of open and interesting questions. Maybe I need more information about who made that vacuum cleaner, what company.
Yeah. But this is like what's happening also. What's everybody's afraid that that Tesla will update my car and suddenly it will crash into the first concrete wall that it sees. Going back to what you've been talking about, how do you actually evaluate the confidence of a model? You mentioned that it's important to see the decision in the decision-making models. It's important to see the confidence scores and confidence levels. So how do you actually benchmark and evaluate the confidence of a model?
So with a lot of these problems, so researchers try to come up with benchmarks of studying these type of scenarios. There are hard benchmarks and easy benchmarks, but you basically want to evaluate the model against the situations the model was not trained for, while the situations are sort of realistic and sort of quite likely to be encountered in a real world settings. And I think the big challenge is to being able to disambiguate simply incorrect predictions of the original model from the situations which I have not seen before, right? And this is sort of a subtle distinction because this sort of depends a little bit on the problem domain. But one needs to account for this in actual design of the models and the architectures. So you need to use sort of reliable confidence estimation models. You need to kind of combine different features. You need to sort of have some categories which account for this unknown. And then what is unknown may be things which you don't care about understanding, but the other type of unknown is the things you really care about. You just have not seen them before. And these two things typically differ, right? So you can have a lot of things which you are happy to throw into an unknown category because you don't care about it for your application, but you may have things which you have never seen before, which you really care. Like, if you have some big obstacle in front of you, this can be very important for safety, but you may not care about the fact that they installed a new set of lamp posts on the side of the road, which are different than the ones you've seen in the training stage, right? So it's this type of variations that need to be considered in the design.
Thank you. And we have another question going back to the explainability. If we had good explanations of the decisions of the model, how could we actually use them to avoid or minimize bad decisions or even accidents caused by the model? What's the feedback loop, so to speak?
So I guess, this type of feedback loops vary from the application domain to application domain. So I think in autonomous driving, this ability to recognize bad decision and situations basically is used for going back and kind of retraining the model, adapting it, and so forth. And then, there is this whole process in place when a new model can be released and what type of testing needs to be done. So you can think of these bad situations as opportunities to simply or gather more data and then over time to make the model more reliable. In other situations which are not so safety critical, so for example, in situations where you have some question answering systems with natural language processing, there's a lot of interest in designing interfaces where the system can kind of intelligently converse with the human in order to gather the additional information so as to increase the understanding and of a particular domain and sort of get sort of better answers. So these are sort of two application domains which are the different ends of the spectra, but in one case you can use this natural language processing and understanding queries to use humans to improve the system in a particular domain and say remove some of the ambiguities of the natural language. In the autonomous driving setting, it's more kind of going back to the simulation and using the new data for improving and updating the system.
Yes, thank you. We still have one question that I'm very interested in as well, because we see it in facial recognition as well. We see a growing trend in the, let's call it, anti-surveillance fashion to trick CCTV cameras into not seeing you, special codes or special pictures that make you invisible to facial recognition especially. Do you see this as a future obstacle or issue for autonomous vehicles? And I can totally understand the question, because it's one thing that the CCTV camera can see you, but if an autonomous vehicle can't see you, that's quite another problem. So do you see it as a future problem, this, let's say, called anti-surveillance fashion that's basically attacking weak spots for machine learning models?
Yeah, I think, so this is not one of the top problems in the autonomous driving, partly because I guess there is some expectation that the release of these systems will be somehow regulated, and you cannot sort of easily hack these cameras in order to sort of cause harm in these type of settings. But another thing, and I'm gonna kind of diverge a little bit just because I've recently encountered this scenario, which was a little bit more worrisome, is this sort of abilities to generate these deep fakes, right? So you have these realistic videos which you cannot basically, you cannot distinguish it from real humans. So you can have these imposters acting as you. And, in both kind of scenarios where they're trying to help you, or in scenarios where this can possibly cause some harm. And I think this is something which, these technologies are very mature. I think, there were scenarios that, for example, somebody was interviewing for somebody on the behalf and somebody else actually showed up for the real job. So these are sort of scenarios which have actual consequences. So yes, so I think we need to kind of think about how to make these technologies secure. I think every advancement in improving the quality of these deep fakes is typically followed by an advancement of actually discovering that something is a deep fake or not. And so this is kind of this continuous cycle between the developers and the adversaries, which I think will likely continue.
Yeah, I think in this case we can also expect that people somehow want to be seen by the autonomous vehicle, so they are actually not run over. So So this is but we are talking about a human factor in in decision making and unpredictability. So anything can happen. Thank you so far. We will probably have some more questions for you. I will just now switch to Jakub for a bit so that you can have a bit of a rest. First, we had the question on hold. Can we? Do you want to get back to that?
Yes, I still remember the question.
Yeah.
My understanding has been always that in this financial sector, it's crucial in order to make a good trading strategy. It's always important to go beyond the observed data and include additional factors, either of economical or political nature. My impression here was that you just based your predictions on the recent data that was observed, right?
Yeah.
So do you think there are ways to extend these AI models by incorporating properly, if available, any additional information?
I will just repeat for the people in stream. The question basically was that you only mentioned in your model the price data, but there are other factors to take into account when trading, for example, political, economic data. Is it important to incorporate them into models? What's your opinion on that?
Yeah, so like factor models were very, very popular, still very popular. Truth is that when using these kind of, let's say, economical data or financial statements, you are kind of using information that somehow we believe is contained in the price data itself. Mm-hmm. It is one of the assumptions of the market. That one of the many assumptions of the market is that it's efficient, right? And that the price is one of the cleanest ways of how we can observe what the opinion of the market is on a certain asset, let's say. And to be truthful, the sources for this fundamental data, economic data, data about the companies themselves, for example, that go into these baskets of indices, they could be used, they could be explored. It's just not the way that we went with, because it has already been done so many times, and these models are being used currently. So it is something very simple. Obviously, there are other data sources that you can explore, not just the financial statements and P/E ratio, earnings per shares, whatnot. But you can use data when you go with the higher granularity. Well, high frequency data about the order book, about the orders lying somewhere, the limits, stop losses. These are all the actually very influential probably factors that could give you further edge. So yes, we will definitely be looking at other data sources and even these financial statements or economic data.
Getting to another question, how often do you retrain the model that you are using? Or is it just trained one time and then just performs inference with the old data?
So possibly one of the other things, about the market is always changing. So there are millions of actors that are acting against each other, and the underlying process is changing, as let's say with machine learning being added to the mix. So you actually expect the model not to perform very well for a very long time, right? Mm-hmm. So we do these retrainings, and there is an obviously one, because we are trading these future contracts. There is an obvious period where a retraining should take place, and that's where a future contract rolls over, and that's for these Euro stocks futures or S&P futures. That's usually quarterly. Mm-hmm. So that's when the contract is actually due. That's where a new contract starts. That's the contract nearest in the front. So a quarterly basis could work, and yearly basis could probably work as well. Obviously not hourly or daily, since our data is of the daily periodicity, but could be done weekly as well.
Okay, and since you just mentioned it, what is the reason behind using just price data on daily granularity?
Simple. First and foremost, the availability of that data. So you don't have to go for higher frequency. Then with that are the procedures that you have to do on top of that. So when you're using the price data of a daily frequency, your data set is relatively small. Once you go into, let's say, minute sampling frequency or a TIG market kind of data, or the trades themselves, you have terabytes of information that you would need to be processing on, let's say, even daily or weekly basis. It's quite a huge amount of data. So this is like the first one, and the availability. And the second reason is that there are challenges associated with higher frequency data or different sampling techniques.
Thank you. Can we go back to Ms. Koshitzka now? We have actually a question that's quite popular, and that is, which programming language are you using to train and improve your models?
We do most of the programming in Python. I mean, this is sort of the language of choice. I mean, partly due to the availability of a lot of modules and libraries for this type of problems. But for kind of more application-specific settings, especially in robotics, C, C++ is definitely not forgotten and a very integral part of the design.
Okay. We have another question on computer vision or vision machine learning. Do you think the shift to higher privacy will significantly affect the advance of vision in machine learning? Can the artificial data or synthetic data keep the performance that we have currently? This is something actually we need to address in facial recognition as well, because collecting of the data is becoming more complicated.
Well, the idea of the synthetic data is more this ability to kind of study different factors, right? So it's not necessarily going to give you an extra edge in the recognition performance, but when it comes to at least categories, and by categories I mean male, female, or gender, it can, or race, it can give you some ability to have the data sets a little bit more biased, right? So that way you can avoid misclassifying some of the examples due to the biases in the data set. Now, okay, so this is just a comment on the recognition, not necessarily related to the privacy. So what was, can you elaborate again on the privacy question?
The question was whether the shift to higher privacy, the let's say the focus on higher privacy or protection of personal data will significantly affect the advance of vision machine learning.
I think I view these things sort of quite orthogonal, right? In some sense that, you know, so people will be developing sort of higher quality. And if you mean by privacy, do you mean these kind of deep fake scenarios that you want to be able to...
I'm not sure if the author of the question is here, so I'm not really sure, but I would say that it's pertaining to the plan of, or let's say attitude of people to protect their personal data, so not sharing the data with others and protecting themselves from the scenarios where their data can actually be captured, for example, CCTV cameras and so on and so forth. So
I mean, at the moment, I do not see a direct connection. I mean, but again, this very much depends on the domain, right? So there are certain data which cannot be synthesized because it's extremely challenging, right?
Yeah.
And so the faces are in some sense an outlier in this category of kind of the visual world, which is extremely rich. Yeah, so I do not see that this is going to kind of significantly affect the performance of, at least in the applications I'm familiar with,
Yeah,
of
thank
this
you.
machine learning.
And we have one more question for you. Do you think that federated learning would address some of the issues of continuous learning, for example, by collecting data from individual vehicles for future retraining?
Yes, so this is definitely a kind of a very exciting field. It is not entirely clear whether it's exactly applicable to autonomous driving setting, partly because, well, so in some sense, some of these things can be computed in the edge, but they have to be somehow kind of reconciled by the companies at the end, which are managing the software which is being deployed in the vehicles. But this federated learning is definitely a sort of very exciting area. And, the data which is being collected by many vehicles is sort of being collected and used. And it is indeed an interesting question whether some of these updates sort of could be done on the edge. I mean, the real question is how to kind of correctly then reconcile all these updates and how they will contribute to the final models. I think, right, so this sort of requires some thoughts about, what would be the infrastructure of this type of systems, because in some sense, if you drive in one geographical area, and that's where you do all the driving, you have a very good chance of actually learn a very good model of that area during different weather conditions, traffic situations, times of the day, and so forth. And so I think the direction is will be more likely to move to have this kind of geographically specified models, and this is pertaining to autonomous driving, as opposed to this desire of having these like globally valid models, right? So I suspect this would be sort of more meaningful direction to go.
Thank you. And
when it comes to updating things.
Yeah, we have one question that kind of ties with this as well. And how do you address the domain shift problems in applications such as autonomous driving? For example, changes in weather. Do you have to plan for it beforehand? Do you have maybe different models? What's the plan, the process?
Yeah, there are typically different models. There are also approaches which are sort of trying to be invariant with respect to some of these factors, such as time of the day and then the change of the season. So not all the techniques rely on visual measurements. So in situations where the visual content changes dramatically, you can rely on other sensing modalities. But there's definitely, this is definitely being studied, this either in visual domain or in other domain. But one idea is to use these multimodal systems where you also use range measurements in addition to vision measurements, which do not suffer so much from some of these domain shift factors.
Thank you. I have one last question for you because I know that you need to be leaving for your next appointment. So what do you think we need to actually achieve in AI in order to be able to trust the AI in major decisions such as court sentencing or medical decisions? What actually has to be done so that people trust it?
These are sort of very challenging questions. So I think the transparency component is important. I think, from the machine learning perspective, you have features and models, right? But at the end of the day, they're just numbers. But there are these often difficult to quantify aspects of behaviors which do not are sort of not accounted for in these modeling formalisms. And so having some kind of transparency in how the model makes these decisions is definitely going to be kind of increasing the trust of these systems. And, like this is specifically in the court decisions, you can have, say, a lot of attributes of a, case of a person, which would indicate that the person is a violator, but in some sense, if it is a first-time offender, plus some other subtle attribute, which is really hard to quantify, right? I don't know, maybe it's like a community person or, something which really pertains to the person's personality,
Yep.
which can dramatically affect the human perception of the person as a violator or not. These are kind of difficult scenarios. So I think it will take a while. One should view these systems merely as sort of a recommendation systems. I think it will, I think human will continue to be involved in decisions like these.
Yeah.
But I think it is important to kind of be educated to which level these systems can be trusted and really sort of understand a little bit the workings of these systems in order to kind of take the predictions sort of in the right way.
Yes, thank you for your answers. I think it's a good way to actually finish this part, that we'll still need to have a human somewhere in there to actually make sense of these predictions or even help to generate more trust. We still have some questions for Jakub. Ms. Koshitzka, thank you very much for having time for us. Anybody who has any more questions, please send them to us. We will send it to Professor and we will send it in a follow-up email so they are not lost. And we will still continue for a bit the discussion with Jakub. Thank you. It's been a pleasure.
I think I'm going to say goodbye. Thank you very much.
Yeah, see you in another session. Thank you. Bye.
Bye.
Jakub, you showed the graph that the algorithm seems to work better in bad times. You shown the example of a post-COVID situation. Is it better than the market average in good times as well?
Yeah, great question. So what they actually there are some things that we can tune with the model itself. We are doing kind of selections of the trades that we are going to be involved in. We're going to have exposure, and what this causes is that we are trying basically to time the market, but it is very hard for something that is timing the market and not being in the market all the time to outperform the index which is in the market all the time, right? Mm-hmm. So in general, when we did our walk forward, out of sample, out of time, these simulations, back tests, so what we saw is that because it tends to how would I say it? Asymmetrically reduce the downsides. Mm-hmm. It takes quite a lot of time for the market to catch up with the model itself on its, let's say, most aggressive settings. But in general, I think this is a very good observation. So it is asymmetrically better at bad times, but it does not reach the let's say the market participation, buy and hold, let's say participation in the market in the good times, mm-hmm. because then your bias is towards the upside, and you are choosing from the upside, to take only certain trades.
Yeah, we also have questions about basically explanation of the model. One would be, did you try to find the causes or patterns in especially bad predictions?
Yeah, there is something that I really hate about the model, and it's not the model itself. It's something that has to do with these volatility estimates. So volatility is this weird beast. We know that it kind of clusters, and that there are these like positive correlations. You know, a very high volatile day will be probably followed by another very high volatile day. We just don't know in which direction. So we have a very high, let's say, a loss in one day, very high profit in the next day. And one of these problems it does is that we are in a position, let's say we open a trade, and then the trade closes during the day, but the market, let's say, goes up, yeah? So it stops you out because the volatility estimate was incorrect in predicting, let's say, higher these to widen these boundaries that we have on take profit and stop loss. So this is something that we know that is especially bad, and it's not the prediction itself, right? The predictions would predict, let's say, the market go up, but you know the trade will stop us out, and sometimes it's really just by small number of points in those future contracts, which is really shameful. And that's what I'm actually currently working on most of the time, looking at how different volatility estimates can help to manage these, you know, wider, let's say, intraday volatility events.
Mm-hmm. Yeah, and
what
the
about
other part?
Yeah.
The other part. What was the explanation for your model performing during the COVID outbreak, where you basically kept a nice smooth line?
I think part of that is that the model is kind of volatility averse. It learned to ignore times where the volatility is higher, and it generally kicks back into action once the volatility starts to be low enough. But together with that, and the question that is still on the board, you know, the explanation extracted from the model. That's what we are trying to do. Kind of use normal trading strategies to describe what the model might be learning. You know, some sort of approximate trading strategies to that machine learning algorithm. And what it seems to me, what I've extracted from the model is that it is kind of like buy the dip machine, right? So it does really like to buy the dip, but not in times of extreme volatility. You know? It's scared of the extreme volatility. It will risk somehow in the volatility, and it also likes some sort of patterns to be formed on the chart itself.
And we have, what time sampling of price did you use, and did you try deep learning? I think this has already been answered by your presentation, because these are the really old questions. Just let's finish quickly with the deep learning and neural networks. So why aren't they applicable in this models?
Even like very shallow neural networks, or you know, the recurrent networks or transformers of some sort, we tried. But it's actually very hard to make them fit. That's the first problem. We don't have enough data for the daily data to have such a large model be applied to the problem, to the data set. So yes, we tried it. It didn't work out.
Okay. So and there's a nice question, and let's finish with that one. Do you share your information and experience with other banks about the automated trading?
So I would not call it automated trading, because automated trading would mean that there is some sort of execution engine tied to the model itself, and you know, we would have the model close and open position on its own. So it's not automated in a sense. It's very manual. There is a person that has an advice of a model and is going to perform that action and buy an order on the spot and sell the order on the spot when the model says. But from that sharing of experience, I think this was presented, this use case for the Tatra asset management was presented. There was some sort of conference of asset managers in Slovakia, asset management funds, and that's where they went out with, you know, okay, this is something that we are working on, we are using. But for like, let's say the deep dive, you know, the information that you would be trying to maybe work on for you are working on for a long time. I don't think this is being shared.
Yeah. Okay, thank you, Jakub, for your answers. For the people who are here, you will still have the chance to talk to Jakub after we finish with the stream. It's been very pleasurable to meet you for the first time and in such a high number. So I'm very grateful that we are really starting to build a better AI community in these meetups. The next meetup should be at on the 22nd of June. Probably here, probably somewhere else. We'll keep you updated. So just write us an email and we will be sending you newsletters so that you are informed. Once again, big thanks to Jakub from Tatra Banka and to Professor Jana Koshitzka from George Mason University. And big thanks to Kinit and HubHub who provided us with the place and for Innovatrix. Thank you and goodbye and have a nice evening.